Hello, everyone. This video, we will look at section 4.4, exponential equations. We have three objectives that we will look at today. The first is use like bases to solve exponential equations. Then we will also use logarithms to solve exponential equations. And finally, look at some applied problems involving exponential equations. So let's take a look at the first objective. Okay, so in the previous section, we had taken a look at the definition of exponential functions. So in this form, where you have the a with the base b to the t power, where your base had to be greater than 0, but not equal to 1. And your initial value is also not 0. An exponential equation is one where a variable is part of the exponent. So for our first example, we have the exponential equation 3 to the x power equals 81. And this is exponential because our x is in the exponent, the variable is in the exponent. So many exponential equations can be solved by writing both sides of the equation as a power with the same base. So to solve 3 to the x equals 81, we can also rewrite this as 3 to the x equals 81 can be expressed as 3 to the 4th, because 3 times 3 times 3 is 81. And then because it's the same base, we know that x has to be 4. So this was a simple case. So let's look at the one-to-one property of exponential functions, which we had applied here. If you have the same base, you can set the exponents equal to one another. So for any algebraic expressions, s and t, if you have some base to the s power and it equals the same base to the t power, you can always conclude that the two powers, the s is equal to t. Okay, so let's look at example 1 when we have the same base. So in this case, you have the 2 to the x minus 1 and 2 to the 2x minus 4. According to the one-to-one property, we can say, okay, the bases, they're the same, so we can set the exponents equal. So x minus 1 is set equal to 2x minus 4. Then it becomes a regular linear equation where we can solve here by subtracting x on both sides to cancel this x. And then here we can add 4 on both sides to cancel this 4. And so we would get x is equal to 3. Okay, so that was an easy case because the base was already the same, but most equations are going to have a different, it's going to have a different base. Well, it looks like it has a different base, so we have to express both sides so that it's written as the same base. So for the second one, we have 256 equals 4 to the x minus 5. Now, at first glance, 256 doesn't look like it can be rewritten as a power of 4. So I played around with my calculator a little bit to check and found that 4 to the 4th is 256. Then we can set that equal to 4 to the x minus 5. And now we've succeeded in getting the same base. So according to the one-to-one property again, once we have the same base, we can just set the exponents equal to each other. So we have here the 4, and then we can set that to x minus 5. And then we can add 5 to both sides and get x is equal to 9. Let's take a look at number 3 now. We have 8 raised to the x plus 2 and then 16 to the x plus 1. 8 and 16, it's not written as the same base. So let's make it look like that they have a common base. So 8 can be written as 2 to the third power because it has the x plus 2 there originally. Let's put that next to that 3. 16 can be expressed as 2 to the fourth, and we can write x plus 1. Because it has the same base, we can now set the exponents equal. 3 to the x times x plus 2, and then 4 times x plus 1. Let's distribute. We get 3x plus 6 equals 4x plus 4. Let's subtract the 3x over to cancel. And then we can subtract the 4 here to cancel that 4, and we get x is equal to 2. You can always plug your answer back in to see if you get the same thing on both sides. Okay, let's move on to number 4. We got 2 raised to the 5 minus 3x equals 1 over 16. Again, our goal here is to express both sides with the same base. Here we have 2 to the 5 minus 3x. Can't really simplify that. But with 1 over 16, we know that 2 to the fourth, right, from the previous problem is 16. But if you have 1 over 16, we can express that as 2 to the negative fourth. And that'll give us 1 over 16. So 1 over 16, let's write that as 2 to the negative fourth. And now we've done expressed both sides with the same base. So let's now set 5 minus 3x equal to negative 4. And then we could subtract the 5 over, get negative 3x is equal to, oops, I already did that in my head. This 5, and then that becomes negative 9. Then divide by negative 3, and we get x is equal to positive 3. Number 5, I would like you to try on your own, and then we'll go over it in class together. Okay, but it's the same idea with 1 over e. Try to write both sides with the same base. Okay, moving on to 6, we have 2 to the 5x equals square root of 2. Now you see that they're both 2's, but the right-hand side, it is not expressed as the same base, right? There's no exponent there. But we know that square roots can be written as the 1/2 power. And we'll just keep the left-hand side the same. And now we have 2 to the 5x equals 2 to the 1/2. So then we can, because it's the same base, set the 5x equal to 1/2. And here, either we could divide both sides by 5, or because the right-hand side is a fraction, it's going to multiply that side by 1 over 5. And then we have x is equal to 1 over 10. Okay, last one, number 7, 4. We have that times 3 to the x minus 24 equals 300. Before we do anything, raise or try to get it to the common base, you want to isolate your base. And to do that, we're going to add 24 to both sides. And then we get 4 to the 3x equals 324. Now, some of you may have thought to multiply this 4 and the 3 together. We can't do that because this 3 has an exponent of x. So we can't multiply the 4 and the 3. We just have to keep them separate. Now, to get rid of this 4, we can divide by it because 4 is being multiplied by the 3x. And the 4 can be canceled by dividing. We have 3 to the x power equals 324 divided by 4 is 81. And this is an earlier problem that we had. And then that is equal to 4. All right, that is the end of the first objective, and we'll continue with solving exponential equations using logarithms.